Hi, I am Sanjay Patel. In this video, we are going to discuss convergence and divergence of infinite series using definition only. Uh, First of all, let us recall quickly what is the meaning of series and convergence series. We have defined in our previous video an infinite sum denoted by the symbol sigma n equal to 1 to infinity, which is given by a1 plus a2 plus a3 and so on up to infinite terms, is called a series. This is called a series or infinite series, right? And if you want to define the convergence or divergence of this series, first of all, you need to consider a sequence of partial sum, which is defined like this. We know that we take Sn is equal to a1 plus a2 plus a3 up to an, and this we define for every n belongs to n, or n is equal to 1, 2, 3 and so on. So we know S1 is a1, S2 is a1 plus a2, S3 is a1 plus a2 plus a3 and so on. Finally, the nth term in general we define as Sn is equal to this. So we obtain a sequence Sn. This S1, S2, S3 and so on. This is called sequence of partial sums, which we write in short as Sn. So it is called sequence of partial sums of the series. Partial sums. Okay. Then if the limit of this sequence exists, if limit n tends to infinity of Sn, this limit exists, and suppose that limit is some real number s, finite real number s, then the series sigma n is said to be convergent. So this is the definition of convergent series. We'll write in short as CGT, convergent series. Okay, and the value of this S is called the sum of the series. This S is called sum of the series, and we write it as sigma n is equal to 1 to infinity is equal to S. So in this video, we are going to discuss convergence and divergence of series using this basic definition. Okay. Before we proceed, let us note one more thing. If we have, say, Sn is equal to a1 plus a2 plus a3 and so on up to an, then we can write Sn minus 1 as the sum of the first n minus 1 terms, that is a1 plus a2 plus a3 up to an minus 1. And if you subtract these two, then you will get Sn minus 1 is equal to what? An. So all will be cancelled, okay, up to this, and only this term will be left. So Sn minus 1 is equal to An. So given the series formula Sn, suppose if we know the sequence Sn, then you can find the original sequence An, which is associated with the given series. So for example, suppose if I consider, for example, if we know that Sn is equal to n square, suppose Sn is equal to n square, okay, for some series sigma an, where n is equal to 1 to infinity, then we want to find the original sequence an. So in that case, we can write an is equal to Sn minus 1 using this formula, and this we'll get now from this given sequence Sn of partial sums. Sn is equal to n square and Sn minus 1 is equal to n minus 1 square. So if you simplify, what you will get is n square will be cancelled, and you will get a 2n plus 1. Okay, so that means the original sequence an is 2n plus 1, and therefore this series sigma n is equal to 1 to infinity is sigma 2n plus 1 to infinity. Okay, that means this is the series of odd numbers. So I can write that is sigma an in this case is say 1 plus 3. Either if you take n equal to 1, the first term is 3. So 3 plus 5, 5 plus 7 plus 9 and so on. If you put n equal to 1, 2, 3 and so on, so then you will get this series. So given the sequence Sn of partial sums, you can find out the original sequence an or the corresponding series sigma an. It is also true the other way, which is very simple. If you are given an, it is equal to 2n plus 1, you can find Sn, which is very simple. That is 1 plus 2 plus 3 up to, rather not 1 plus 2, but 1 plus 3 plus 5 and so on up to n 2n plus 1. And then you will get the sum as n square. Some of the first n odd numbers is n square. Okay, so that is not point of interest here. What is we are interested in is how to check convergence of a given series using only this definition. So given a series sigma n, first we will find Sn and then we will take the limit of the sequence Sn. If that limit exists, then we will say the sigma n, the series is convergent, otherwise it is called divergent. And in the case in which limit exists, that number, this S, which we denote by this sigma n equal to 1 to infinity n, is also called the sum of this infinite series. So let us begin by taking the first example. So let us consider the first problem. Discuss convergence of the following series, rather following infinite series, using definition, and find the sum of the series, if exist. If exist means if the series is convergent, then we need to find the sum also. Otherwise, we just say it is not convergent or say divergent. So let us start with the first problem. Say problem number 1. I am taking this the series sigma 1 upon say n into n plus 1. This is the simplest one. N is equal to say 1 to infinity. We want to discuss the convergence of this series. Okay. So let us solve this. Here, the series sigma n equal to 1 to infinity is sigma 1 upon n into n plus 1, n is equal to 1 to infinity. Okay. So that means we have an is equal to 1 upon n into n plus 1. We know what is Sn. To discuss the convergence, we need to find Sn, which is a1 plus a2 plus a3 up to an. But before we find Sn, let us express this as a say some partial fractions, and you know very well how to do that because you have done so many problems of integration using method of partial fractions. So this we can write as say, let us try to write directly. This is say I can write n here and n plus 1, okay, and 1 upon n. Suppose if I put 1 here and subtract this, then n plus 1 minus n, that will be n plus 1 minus n will be what? 1 only. So this we can write as sum of these two partial fractions. Okay. So this is true for n is equal to 1, 2, 3 and so on. Now I can write a1. Yeah, a1 is equal to 1 upon 1 minus 1 upon 2. What is a2? a2 is 1 upon 2 minus 1 upon 3, putting n equal to 1, 2, 3 up to n, because I want the sum of the first n terms of this. So 1 upon 3 minus 1 upon 4 and so on. The last term I would like to write is an. So an is given by 1 upon n minus 1 upon n plus 1. Okay. Now let us add all this. And if you add, then this is a1 plus a2 plus a3 up to n. So you will get Sn, that is a1 plus a2 plus a3 up to an, and which is equal to sum of all this. So here if you observe, then this 1 upon 2 gets cancelled, 1 upon 3 and so on. This 1 upon n will also be cancelled. So what remains is only this first term, that is 1, and the last term, that is 1 upon n plus 1. So this is equal to 1 minus 1 upon n plus 1. So what I have proved here is the sum of the first n terms, a1 plus a2 plus a3, which we call Sn, is actually this number. And this is true for every n. So Sn is equal to 1 minus 1 upon n plus 1. 1 minus 1 upon n plus 1. So therefore, limit of Sn as n tends to infinity, now it is very simple, is equal to limit of this sequence, that is 1 minus 1 upon n plus 1. And as n tends to infinity, n plus 1 also tends to infinity, and 1 upon n plus 1 tends to 0. This 1 is constant, so it will remain as it is. So 1 minus 0, and this is equal to, say, 1. So we can say that limit of Sn exists, and it is some finite real number. This is some finite real number. And that means the series is convergent. Therefore, sigma an, that is the given series, sigma 1 upon n into n plus 1 is convergent. And not only that, we can also write the sum sigma n is equal to 1 to infinity of 1 upon n into n plus 1 is equal to 1. The sum of this series is 1. You can also write this series, it can be asked this way also. Suppose if I write in the other form, expanded form, and this sum can also be asked in this way by putting n equal to 1, 2, 3 and so on. So 1 upon, say, 1 into 2 plus, for n equal to 2, 1 upon 2 into 3 plus 1 upon 3 into 4 plus and so on. So they can ask also this way, okay, prove that this series is convergent and find the sum. Okay, let us go to the next problem. So problem number 2. I am going to take a similar example. Say the series is given by, so 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus 1 upon 9 into 11 and so on. Discuss the convergence of this series. In such a case, we can do one thing, that try to write the general term of this series. So here, how to write the general term means we want to express this series in the form sigma an, n is equal to 1 to infinity, and for that we should find what is an, and that can be done by observing this term. This is the first term, say a1, this is a1, this is a2, this is a3. So a1 is 3 into 5, a2 is 5 into 1 upon 5 into 7, a3 is 1 upon 7 into 9. So just observe these first numbers in each denominator. So this is 3, this is 5, this is 7, this is 9. Okay, so it is an arithmetic progression or arithmetic sequence. The first term is 3, okay, and the difference is 2. 3 plus 2, 5, 5 plus 2, 7. So I can write down the first numbers in this product as, first of all, difference is 2, so 2n, and we want the first term to be 3. So putting n equal to 1 here, what we get is 2 into 1 is 2, but I want first term to be 3, so I will add 1. So what I can write here is this is equal to sigma 1 upon, say, 2n plus 1 into, for the second numbers, that is this 5, 7, 9. Here also the difference is 2. 5 plus 2, 7, 7 plus 2, 9, and so on. So it is also an arithmetic sequence. The difference is 2. So first we write 2 into n. Now by putting n equal to 1, what we get is 2 into 1, that is 2. But I want the first term here as 5. So I should add 3 to this. And that gives me the nth term of this sequence of the second numbers in the denominators, that is 5, 7, 9, and so on. So I can write it as 2n plus 3, correct? So this series you can express in the general form in this way: sigma 1 upon 2n plus 1 into 2n plus 3. Fine. Okay. So this implies an is equal to 1 upon 2n plus 1 into 2n plus 3. Now this I want to express as a sum of partial fractions in order to simplify easily. So this I will do directly. If you don't understand, you can write this expression as a upon 2n plus 1 plus b upon 2n plus 3, and then find the values of a and b. Let us try it directly. So first of all, I will write one linear factor, that is 2n plus 1, and another linear factor 2n plus 3, like this. Okay, and we'll think that what to adjust in the numerator. We do not want n in the numerator here, so, and we see here 2n is there, so I'm just keeping minus sign and putting 1 1. So when you simplify and take LCM, that 2n and 2n will be cancelled, and you get 3 minus 1 is equal to 2. When you take the LCM, first here you will get 2n plus 3, and then minus 2n plus 1. So this 2n will be cancelled, and this 3 minus 1 is 2. So 2 will be left in the numerator, but we do not want 2 there, so I'm writing 1 by 2. Okay, so an can be expressed in this form. Now, in order to discuss the convergence, we should find Sn first, and Sn means a1 plus a2 plus a3 up to an. So let us consider what is a1, a2, a3 here. This is true for every n belongs to n. Remember. So I am taking a1 is equal to 1 upon 2 into 1 upon 3 minus 1 upon 5. You put n equal to 1 here, so 2 into 1 plus 1, that is 3, and here 2 into 1 plus 3, that is 5. And plus, then a2, the next term, is 1 upon 2 into 1 upon 5 minus 1 upon 7. Again, putting n equal to 2 here, you will get 2 to the 4 plus 1, 5, and here 4 plus 3, that is 7. A3 is, now you can understand and write directly without looking at that formula by the symmetry or using this pattern. And if you continue like this, we want to find a1 plus a2 plus a3 up to an. So the last term an I will write directly as we have written above. So that is 1 upon 2, 2n plus 1 minus 2n plus 3. Okay. Now adding all this, what do we get here is a1 plus a2 plus a3 plus an on the left hand side. And here on the right hand side, when you add all these brackets, 1 upon 2 is common, and this 1 upon 5 is cancelled, 1 upon 7 will be cancelled, this will be cancelled, and this term, the previous term, will be cancelled with this thing. So what is left is only 1 by 3 and this 1 upon 2n plus 3. Okay, so this implies Sn, that is a1 plus a2 plus a3 up to an, is 1 by 2 times 1 upon 3 minus 1 upon 2n plus 3. Now we can take the limit here and find Sn. So limit n tends to infinity Sn is equal to limit n tends to infinity of 1 by 2 into 1 upon 3 minus 1 upon 2n plus 3. Okay. So this is a very simple limit problem, just as n tends to infinity, 1 upon 2n plus 3 tends to 0. So we'll get the value of this limit as 1 upon 3 minus 0 into 1 by 2, that is 1 by 6. So this limit exists, and it is a finite real number, and therefore the conclusion is the given series sigma n, this series is convergent. Not only that, the sum of this series is the value of this limit, that is 1 by 6. So therefore sigma n is convergent, and the sum of this series, so sigma n 1 to infinity, is 1 by 6. Okay. Let us take another example and see whether it is convergent or divergent. So the next problem, number 3, I am taking this example, sigma log of 1 plus 1 by n, okay, and n is equal to 1 to infinity. We want to discuss the convergence of this series using definition. Okay, so here sigma n is equal to 1 to infinity is sigma log of 1 plus 1 by n 1 to infinity. So that means the nth term an of the original sequence is log of 1 plus 1 by n. Okay, I want to find Sn to discuss the convergence, and Sn means a1 plus a2 plus a3 up to an. Okay, for that I would like to write this log of 1 plus 1 by n in this way, log of n plus 1 upon n, and this I can separate as log of n plus 1 minus log of n. Okay, so what we have proved is an is equal to log of n plus 1 minus log of n. Okay, and putting n equal to 1, 2, 3 and so on in this, what we get, okay, is a1 is equal to log of 1 plus 1, that is log 2 minus log 1. Okay, a2, putting n equal to 2 in this, we get log 3 minus log 2. a3 will be log 4 minus log 3 and so on. And nth term, that is an, will be this only. So an we can write as log n plus 1 minus log n. Now adding all these terms, we see in the right hand side this log 2 and this log 2 will be cancelled, this term and this term will be cancelled, okay, like that. So finally here this log n and this previous term will be cancelled. So adding all this, adding these terms, these n terms, we get Sn, because the left hand side is a1 plus a2 plus a3 plus an, and that we call Sn. And on the right hand side, if we add all this, what is left is only this term, log of 1 plus n plus 1, and this log 1, but log 1 is 0. Still let me write this way, log of n plus 1 minus log 1 will be left, and which is nothing but log of n plus 1, as log 1 is 0. Okay, and now taking the limit of this Sn as n tends to infinity, what we get is very clear. Limit n tends to infinity Sn is limit n tends to infinity of log of n plus 1. As n tends to infinity, n plus 1 tends to infinity, and log infinity is also tends to infinity. So this tends to infinity. That means limit n tends to infinity of Sn does not exist. This limit does not exist, and If limit of Sn does not exist, we can conclude that the given series sigma an, that is sigma log of 1 plus 1 by n, is not convergent. Is not convergent. That means it is divergent. Okay? It is divergent series. In this case, no need to find the sum. Let's take one more example of divergent series. The number 4. Let us consider this one, sigma, say n cube, or let me write this way, say 1 cube plus 2 cube plus 3 cube and so on up to infinite term. So consider this series. We know that this series you can write as sigma n cube, n is equal to 1 to infinity. Okay. To discuss the convergence, first of all, we need to know what is an. So here, sigma an is sigma n cube, 1 to infinity. Okay. And therefore, I can say an is equal to n cube. Now, Sn means a1 plus a2 plus a3 up to an, some of the first n terms of this series. And that implies Sn is given by, say, 1 cube, a2 is 2 cube. Because of this formula, an is equal to n cube. Putting n equal to 1, 2, 3 and so on, you will get all these terms. And the last term is n cube. So this is the sum of the cubes of the first n natural numbers. And we have a formula for this, that is sigma n cube formula. As you know, sigma, you can write, it is sigma I cube, I is equal to 1 to n. And for this, the formula is n into n plus 1 by 2 whole square. Okay. So that is, we have the sigma, that is, we have Sn is equal to n square into n plus 1 whole square by 4. And it is clear that if you take the limit of this Sn, then it tends to infinity. So as n tends to infinity, Sn tends to infinity, because denominator is fixed, numerator keeps on increasing. So you can understand that this will tend to infinity. And therefore, the given series sigma n cube 1 to infinity is divergent. This will write in short now onwards as DGT. It is a divergent series. Okay.